Assalamualaikum. In this video, we are going to present our consequence analysis project for the risk and safety assessment course. We have chosen Petronas Chemicals Fertilizer Kedah Sundian Berhad as the facility for our project. Before I proceed, let me introduce our group members. First, Muhammad Azman bin Muhammad Husnin, then me, myself, Muhammad Ifam bin Khairul Anwar. Third, Siti Nur Azirah Hidayah binti Azhar. And lastly, Nur Safiyah Hani binti Ahmad Tazam. For the introduction, Petronas Chemicals Fertilizer Kedah Sundian Berhad, or also known as PCF Kedah Sundian Berhad, is a company in the chemicals industry. The company size is range between 50 to 200 employees and is a fully owned subsidiary of Petronas. Capacity of daily production of this facility is 1,125 megaton for ammonia, 200 megaton of methanol, 2,000 megaton of granular urea, and 17 megaton of urea formaldehyde. The company is producing fertilizers and the primary products is granular urea with ammonia and methanol as the byproduct in the manufacturing processes. And the facility is supported by steam generation and distribution system, demineralization water system, cooling water system, instrument air system, nitrogen production unit, and also wastewater treatment.
Okay, moving on to the first scenario, the potential events due to ammonia release in air were toxic release, flash fire, and explosion. The model used for this scenario was direct source, assuming the ammonia reactor failure was due to failure of safeguarding equipment. The source of strength, which is the source height is 2 meters, the source temperature was equal to ambient temperature, and the release duration is 60 minutes, with the amount of ammonia released is estimated at 1 kilogram per minute, and the total amount released of 60 kilograms. So based on ALOHA modeling, the level of concern, NOC distance for toxic ammonia release, and flash fire was estimated to be less than 25 meters, where the affected area was surrounding area of facility as listed in table 1 and table 2, and whereby the graph and diagram are illustrated in figure 1 and figure 2. So as we can see in the figure 1, which is the level of concern for toxic ammonia gas release, which is the model run is heavy gas, and the red zone is around 83 meters with 1,100 ppm, which is equal to AEGL3 in 60 minutes. For the orange zone is around 220 meters with 160 ppm, which is equal to AEGL2 in 60 minutes. And the last one is yellow zone, which is around 541 meters with 30 ppm, which is equal to AEGL1 in 60 minutes. So moving on to table 1, which is the level of concern, LOC of flammable area for flash fire. So the model run is heavy gas, and the threat zone, toxic threat zone for this event is, for the red zone is around 10 meters with 150,000 ppm equal to LEL. For the orange zone is around 13 meters with 90,000 ppm, which is equal to 60% of LEL and equal to flame pockets. And last one is yellow zone with 31 meters in with 15,000 ppm, which is equal to 10% of LEL. So we proceed with the table 2, which is the level of concern for overpressure from cloud explosion. So for the threat model, the type of ignition is ignited by spark of flame, and it is uncontested. For the threat zone, the model run is heavy gas, and for the 3 zones, which are red zone, orange zone, and yellow zone, there is no part of cloud is above LEL at any time.
The next scenario of release is the chemical release from a leakage tank. The two chemical releases that have been affected to the human and surrounding are ammonia and methanol. So for the scenario 2, there will be two parts. The first part is for methanol and the second part is for ammonia. So for the methanol, there are three possible events which are toxic vapor gas release, flash fire, and explosion from flammable vapor cloud. The calculated total amount of release was 43,000 pounds methanol with maximum average sustained release rate of 900 pounds per minute. And the methanol will escape as a liquid and form an evaporating puddles that spread to a diameter of 89 yards. So the tank is with a circular opening diameter of 50 cm and with the opening height of 5 meter for hole in the tank. So this is the result from the ALOHA. So the LOC for toxic gas release of methanol through a leakage from a hole in the tank is for the red zone is 223 yards, for orange zone is 497 yards, for yellow zone is 1185 yards. And this is the figure from the ALOHA and the figure from the plot. And the next event is a flash fire. So this is the result from the ALOHA. The LOC for flammable area for flash point for red zone is 48 yards and for yellow zone is 223 yards. There is no red zone shown in the both figure due to its small area. Next is the last event, which is the blast or explosion from the vapor cloud. And it seems like there is no blast from this scenario for methanol because there is no part of the cloud that is above the LEL at any time.
Actually, the second scenario can be happen in ammonia tank as well. For source of strength data, the ammonia tank have the volume of 50 cubic meter and the circular opening diameter was estimated to be 0.0762 meters and the opening height is estimated to be 0.5 meters from the bottom of the tank. Okay, so the ammonia leakage has resulted the toxic vapor gas of ammonia to spread to nearby area of the tank. The gas has a toxic effect that could cause fatality incident in area affected. The toxic threat zone for the toxic gas release from ALOHA is listed and illustrated in table 6 and both figure 7 and figure 8. So we can see the toxic threat zone. The model run is heavy gas and the red zone is estimated to be 2.4 meters with 1000 ppm, which is equal to 8 EGL3 in 60 minutes. The orange zone is 5.2 meters with 160 ppm, which is equal to 8 EGL2 in 60 minutes. And the last one is yellow zone, which is greater than 10 km, which is 530 ppm, which is equal to 8 EGL1 in 60 minutes. So we can see this is the graph of LOC on toxic gas release of ammonia through leakage from a hole in the tank, and in figure 8 shows the individual risk contour for toxic threat zone. Okay, when there was a slight delay of ignition, it will result in second event, which is flash fire from the vapor ammonia gas release. The LOC distance for flammable area was 851 meters from the source tank as shown in table 7 and illustrated in figure 9 and figure 10. So we can see in table 7, the model run is heavy gas as stated before, and the red zone is around 238 meters with 100 ppm, which is equal to LEL. The orange zone is estimated to be 340 meters with 90,000 ppm, which is equal to 60% of LEL and equal to flame pockets. And the last one is yellow zone with 851 meters with 15,000 ppm, which is equal to 10% of LEL. So we can see in figure 9 the shows the graph of LOC unflammable area for flash point through leakage from a hole in the tank for ammonia, and the figure 10 we can see the individual risk contour for flammable area zone.
Lastly, the third scenario is a methanol leakage from a hole in the pipe. This scenario could be considered as the worst scenario event due to its huge area affected. There are again three possible events, which are toxic vapor gas release, flash fire, and explosion from flammable vapor cloud. The calculated total amount released was 156,000 pounds methanol with maximum average sustained release rate of 2,600 pounds per minute. So the source strength data for methanol leakage through a hole in the pipe is the whole area of 491 square centimeter with the pipe pressure of 4 atm and the pipe temperature of 120 Celsius. So this is the result from the ALOHA. The LOC for a toxic gas release of methanol through a leakage from a hole in the pipe for the red zone is 961 yards. For the orange zone is 1.1 miles. And for the yellow zone is 3 miles. It's very big. Okay, so the next event is for flammable or for flash point through a leakage from a hole in the pipe. So for the red zone is 520 yards and the yellow zone is 1,434 yards. And the last event is the blast of overpressure from a vapor cloud explosion through leakage from a hole in the pipe. So there is for yellow zone, which is 388 yards, while there is no for orange and red zone since the LOC was never exceeded.
Now I will explain on the individual risks of our chosen facility. Our facility, the Petronas Chemicals Fertilizer Kedah Sdn Bhd, handled many types of chemicals, and these chemicals need to be handled very carefully. For the first chemical, which is methanol, it is very toxic to humans if swallowed, and its vapor can also cause harm if inhaled by humans. Then the employees who are working to handle the methanol reactor and the pipeline needs to be extra careful to avoid any hazard coming from the chemical. Methanol is also a highly flammable substance. It can easily explode if ignited, especially in a very small closed space. Next, for ammonia, both the phase of gas and liquid ammonia are very dangerous and hazardous to humans. Ammonia is very toxic and can cause death if it is swallowed or inhaled. And ammonia is also a flammable gas where a high airborne concentration can be ignited and pose a significant fire and explosion hazard, especially in a confined space. All the workers need to be extra careful while handling the ammonia tank and ammonia reactor because the ammonia gas can be released when there are some failure in the facility.
Okay, for the societal risk, the potential group of people that would likely be affected is within the area of consequences which are inside of the plant facility. However, the likelihood of the consequences to increase is less since the facility is located far from the housing area. In scenario 2 and 3, the most affected group is the workers who work around the methanol and ammonia tank and its pipeline during the incident scenario. According to Matt Giffen et al., ethanol is being used in the fertilizer because it can be used to help the growth of plant. Less exposure than that in a fertilizer would help to improve metabolic rate of the plant, but more than that, it will become more toxic to leaf tissue. The exposure of methanol concentration is the fertilizer will cause most of the plant mentioned to wilt and die. It will cause a lot of losses, and the facility in the plant also will damage and in the incident. For those workers which being exposed to the ammonia gas, the possibility of fatality is high because ammonia gas is very toxic to human and it is corrosive to respiratory tract.
Okay, so next is the recommendations part. For the mitigation measure and emergency response, we provide three safety concept. First is the inherent safety concept. Second is the gas leak detector alarm, and third is the plan of emergency response. So that these three things can provide the safety to the workers and people surrounding which is near to the facilities. Okay, so for the inherent safety concept, it is the design of feature that can prevent the hazardous situations. For our facility, it is produce the fertilizer. So the hazardous material that we use is the ammonia and methanol. So ammonia is a toxic and flammable chemical. So it is stored below its boiling point with refrigeration. This design feature of refrigeration must have to follow the ammonia characteristics so that can prevent the from the undesired event. Okay, so this refrigerated storage can reduce the release from the tank and reduce the vapor pressure of material. By having this design feature, we can prevent the undesired event from spread off and can guarantee the safety of the workers. Okay, next safety concept that we provide is the gas leak detector alarm. So for the gas leak detector alarm, it is a critical asset for operational safety and efficiency of plants in the industrial sectors. So for the chemical release from the tank is one of the hazards that can harm the workers. For the fertilizer production, most of the accidents is the uncontrolled release. For example, is the uncontrolled release of ammonia. The cloud of anhydrous ammonia is unpredicted and it can spread to the environment by following the air movement. So the workers that treated to this area must be warned of the release. When we have this in the industrial facilities, it can tell the workers if this chemical release or gas leak happen so that the workers will not expose too much to the seriousness of the exposure. Okay, so for the last safety procedure that we provide is the plan of emergency response. So for the plan of emergency response, the industry must have this plan of emergency response. First, they must have the emergency response team, such as the fire brigades and personnel trained in search and rescue. The workers and or emergency response team also should know where is the master point is located so that they can assemble if the undesired event happen. Master point is the part of emergency plan and it is very important point which must be determined and known to the all workers. Okay, hence the industry must develop the steps to overcome in order to minimize the consequence severity resulting from the hazardous event. That's all from us. Thank you and stay safe.